In 1941, German engineers wheeled out a weapon so massive it required its own railway system to move. The Gustav Gun stood taller than a 4-story building and could hurl shells weighing as much as a small car over 29 miles. But this mechanical monster would fire only 48 shots in its entire existence before being scrapped. The Gustav was just one of many bizarre war machines that never fulfilled their intended purpose. Machines that pushed the boundaries between military ambition and engineering madness. From tanks the size of office buildings to submarines that carried their own aircraft fleet, these technological fever dreams consumed millions in resources, only to be abandoned. Today, we're diving into the strange world of military projects that went too far. Picture a tank so massive it could crush a regular Sherman tank like a soda can. This was the Land Cruiser Po 1000 Rat, Hitler's dream of the ultimate land weapon. At 1,000 tons, this steel beast would have been heavier than a fully loaded Boeing 747. Its main guns were literally stolen from a battleship, twin 280mm naval cannons that could demolish fortifications from miles away. The Rat required a crew of 40 people just to operate, and its tracks were so wide they would have destroyed any road they touched. The engineering challenges were staggering. Each track assembly was 6 feet wide and nearly 40 feet long. The drivetrain alone required 8 Daimler-Benz MB500 and 120-cylinder marine diesel engines, the same engines used in German E-boats. These would have generated 16,000 horsepower combined, yet even with all that power, the Rat would have struggled to reach 25 miles per hour. The tank's armor was equally excessive. The front plate was to be 360mm thick, enough to withstand any anti-tank weapon of the era. For close protection, it carried 8 20mm anti-aircraft guns and 2 15mm heavy machine guns. A secondary turret mounted a 128mm anti-tank gun, the same weapon used on the dreaded Jagdtiger tank destroyer. But the Rat had a problem. Actually, it had many problems. Its mammoth size made it an easy target for air attacks. No bridge could support its weight, and its fuel consumption was astronomical. The tank would have needed to be partially disassembled just to be transported by rail. Albert Speer, Hitler's Minister of Armaments, finally cancelled the project in 1943, recognizing it as an enormous waste of resources. This wasn't the only German attempt at a land battleship. The even more ambitious Land Cruiser P-1500 monster would have mounted an 800mm gun, the same size as the Gustav railway gun. The monster would have weighed 2,000 tons, requiring a crew of over 100 men to operate. The sheer absurdity of these projects highlighted the desperate nature of Nazi Germany's military planning in the later war years. While the Rat never made it off the drawing board, the Soviets were developing something equally ambitious: a tank designed to survive nuclear war. The Object 279 looked more alien than armored vehicle, and its bizarre design would push the boundaries of what was possible with steel and engines. The Object 279 emerged from the depths of Soviet engineering in 1959. Unlike the pure fantasy of the Rat, this 60-ton beast actually made it to the prototype stage. Its most striking feature was its oval-shaped hull, designed to help the tank survive the shockwave from a nuclear blast. 4 sets of tracks, arranged in pairs, gave it unprecedented stability and allowed it to cross terrain that would stop other tanks cold. The armor was revolutionary. The hull's elliptical shape wasn't just for nuclear protection. It was also incredibly effective at deflecting conventional rounds. The entire tank was covered in anti-He-8 shields, making it virtually immune to shaped charge weapons. Even the tracks were partially covered by armored skirts, protecting them from anti-tank weapons and debris. Inside, the crew operated in an environment that seemed decades ahead of its time. The gunner had a stabilized sight with infrared capabilities, a rarity in the 1950s. The 130mm main gun could penetrate any NATO tank of the period. The autoloader, another advanced feature, could fire 5 to 6 rounds per minute, faster than most contemporary tanks. But like many revolutionary designs, the Object 279 had fatal flaws. Its complex drive system required extensive maintenance. The overlapping road wheels were prone to jamming with mud and ice. The tank's weight made it too heavy for many bridges, and its width exceeded railway loading gauges. After building just 3 prototypes, the Soviets abandoned the project in 1959. But while the Soviets were building tanks to survive nuclear war, American engineers had an even more radical idea. Why not put the nuclear reactor inside the tank itself? The Chrysler TV-8 would push the boundaries between brilliance and madness, and its design would make even the Object 279 look conventional. The TV-8's nuclear ambitions reflected a broader fascination with atomic power in the 1950s. The reactor design called for a vapor cycle power plant that would heat mercury to drive the tank's electrical generators. Special shielding would protect the crew from radiation, though the effectiveness of this shielding in combat conditions remained questionable. The entire power plant could be removed as a single unit for maintenance or replacement. But the nuclear reactor wasn't the TV-8's only innovative feature. The tank incorporated a closed-circuit television system for the driver, revolutionary for its time. This allowed the driver's station to be completely enclosed within the armored turret, with no vulnerable vision ports. The TV-8 also featured an advanced fire control system with a stereoscopic rangefinder and mechanical ballistic computer. The tank's bizarre egg-shaped turret wasn't just for show. Its rounded surfaces were designed to maximize protection against both conventional and nuclear weapons. The turret walls were spaced armor, with a gap between inner and outer layers to defeat shaped charge warheads. Even the tracks featured rubber pads to reduce noise and improve road speed. Combat survivability drove every aspect of the design. The floating capability wasn't just for crossing rivers. It would allow the tank to survive even if its track system was completely destroyed. The crew compartment could theoretically be sealed against chemical and biological weapons, making the TV-8 one of the first designs to consider these emerging threats. Chrysler built a full-scale wooden mock-up of the TV-8, but the project never progressed beyond that stage. The technical challenges of safely incorporating a nuclear reactor proved insurmountable. The high center of gravity made the tank unstable on rough terrain, and the complex systems would have made field maintenance a nightmare. By 1956, the Army had lost interest, and the TV-8 joined the growing list of ambitious but impractical Cold War weapons. While engineers struggled to make nuclear-powered tanks a reality, other visionaries were looking to the skies with equally radical ideas. And if you thought a nuclear tank was dangerous, wait until you hear about the airplane designed to deliberately ram into enemy bombers at 500 miles per hour. When Northrop engineers unveiled their designs for the XP-79 in 1944, fellow aircraft designers thought they had lost their minds. Instead of using conventional guns or missiles, this aircraft was designed to literally slice enemy bombers out of the sky using reinforced wings. The pilot would fly the XP-79 directly into bomber formations, using the plane's magnesium alloy wings like giant knives to cut through enemy aircraft. The XP-79 wasn't just unusual in its attack method, its entire design was revolutionary. The pilot flew the aircraft lying down in a prone position, allowing them to withstand higher G-forces in combat. The pressurized cockpit was barely larger than the pilot's body, surrounded by 3-inch thick magnesium armor. 2 jet engines, buried within the wing, gave the aircraft incredible speed for its time. But even getting to the testing phase proved deadly. During its first and only test flight in 1945, the XP-79 entered an uncontrollable spin. Test pilot Harry Crosby attempted to bail out, but was struck by the aircraft and killed. The entire program was cancelled shortly after, but this wouldn't be the last attempt at creating an aerial battering ram. The Germans had their own unique approach to aerial combat with the Blohm and Voss BV-40. This aircraft stripped away everything considered non-essential, including the engine. The BV-40 was a glider designed to be turned into combat by a conventional fighter. Once released, it would dive through enemy bomber formations at speeds approaching 600 miles per hour, protected by heavy armor plating. The BV-40's design was elegantly simple yet terrifying. The pilot lay prone in a heavily armored cockpit, peering through a thick armored glass panel. Two 30mm cannons provided firepower, while the small size of the glider made it an incredibly difficult target for bomber gunners. Without an engine, it was cheaper to produce than conventional fighters and required no precious fuel. The Germans built several prototypes of the BV-40, but like many desperate late-war projects, it never saw combat. Test pilots reported that the glider was difficult to control at high speeds, and the logistics of towing fighters into battle proved impractical. Yet the concept of minimalist interceptors would influence aircraft design for years to come. But while Germany and America were designing aerial weapons, Howard Hughes was building something entirely different: the largest wooden aircraft ever constructed. The Hughes H-4 Hercules, better known as the Spruce Goose, pushed the boundaries of aircraft design to their absolute limits. With a wingspan longer than a football field and a tail height equal to a 6-story building, the H-4 remains one of the most ambitious aircraft ever conceived. The H-4's creation story reads like a wartime fever dream. In 1942, the US military needed a way to transport large amounts of cargo across the Atlantic while avoiding German submarines. Hughes proposed a flying boat so massive it could carry 750 troops or 2 Sherman tanks. But wartime restrictions on aluminum meant the aircraft had to be built primarily of wood. Despite its nickname, the Spruce Goose wasn't made of spruce at all. Hughes used specially treated birch, laminated in ways never before attempted in aircraft construction. Every component had to be invented from scratch. No existing aircraft parts were large enough. The plane's 8 engines were the most powerful aircraft engines available, each producing 3,000 horsepower. But engineers worry this still might not be enough. The project dragged on long past its wartime deadline. By 1947, the war was over and Hughes had spent $23 million of government money, equivalent to over $300 million today, plus $18 million of his own funds. Congress launched an investigation, accusing Hughes of wasting taxpayer dollars. In response, Hughes became determined to prove the aircraft could fly. On November 2, 1947, during what was supposed to be a simple taxi test in Long Beach Harbor, Hughes made his move. Without warning his crew or the press watching from nearby boats, he pushed the throttles forward. The massive aircraft lifted off the water, flying for just under a mile at an altitude of 70 feet. It would never fly again. The flight lasted less than a minute, but it proved Hughes' design worked. Yet the achievement was hollow. The era of huge flying boats was already ending, replaced by long-range land-based aircraft. The H-4 became a museum piece, a testament to one man's obsession and the outer limits of wooden aircraft construction. But the Spruce Goose wasn't just about size. Its construction techniques revolutionized wood lamination technology. Hughes engineers developed new methods for creating compound curves in wood, bonding layers together under heat and pressure. They invented new waterproof glues and protective coatings that would later find their way into civilian aircraft production. The specialized tools created just to build the H-4 would influence aircraft manufacturing for decades. The aircraft's control systems were equally innovative. Moving surfaces this large required power assistance, but hydraulic systems of the era weren't up to the task. Hughes' team developed a hybrid system using electric motors and hydraulics, creating one of the first fly-by-wire control systems. The cockpit instruments and controls for managing 8 massive engines set new standards for aircraft system integration. Perhaps most remarkably, the H-4's wooden construction required maintaining precise humidity levels during construction and storage. Hughes built a special climate-controlled hangar just to house the aircraft. Workers had to wear special clothing to prevent their sweat from affecting the wood's moisture content. Even the paint was specially formulated to allow the wood to breathe while protecting it from water damage. The H-4's legacy extends beyond its single flight. Its development pushed the boundaries of aircraft manufacturing, material science, and systems integration. Many of the problems solved during its construction, from laminated wood techniques to electrical system design, would influence aviation engineering for years to come. The aircraft's massive cargo bay design would later inspire the wide-body freighters that dominate air cargo transport today. Yet the H-4 also serves as a warning about the dangers of pushing technology too far, too fast. Like the XP-79 and B-40, it represented an attempt to solve wartime problems with radical engineering. All three aircraft pushed the boundaries of what was possible, but crossed the line into what was practical. Their stories remind us that in aviation, the gap between possible and practical can be as vast as the skies themselves. The financial cost of these aviation experiments was staggering. The XP-79 program consumed millions in research and development before its fatal crash. The BV-40 diverted precious resources from Germany's conventional fighter production. The H-4's massive budget could have purchased an entire fleet of proven transport aircraft. Yet these projects persisted, driven by the eternal human desire to push the boundaries of flight, regardless of cost or practicality. While some engineers dreamed of conquering the skies with wooden giants, others looked to combine the power of aircraft with stealth of submarines. The result would be one of the strangest vessels ever conceived. A submarine aircraft carrier that could surface, launch bombers, and disappear beneath the waves before the enemy knew what hit them. In 1948, Soviet naval engineers proposed something that seemed impossible: a submarine that could carry and launch jet fighters. Project 664 wasn't just ambitious, it was revolutionary. The submarine would surface, open its massive hangar doors, and launch fighters using a steam-powered catapult, all in less than 15 minutes. Then it would disappear beneath the waves, leaving enemy radar operators wondering if they'd imagined the whole thing. The engineering challenges were mind-boggling. The hangar had to be pressurized to prevent seawater corrosion, yet able to withstand the crushing depths. The aircraft launch system needed to work perfectly the first time. There would be no second chances in combat. The submarine's size, over 350 feet long, made it larger than most surface ships at the time. But the Soviets weren't the first to dream of underwater aircraft carriers. The Japanese had already built and deployed their own version during World War II. The I-400 class submarines were technological marvels, capable of carrying 3 aircraft in a watertight hangar. These boats could travel 37,500 miles without refueling, enough to circle the globe 1.5 times. The I-400's aircraft were specially designed Aichi M6 A1 Seiren floatplanes. Their wings and tail surfaces could fold up like origami, allowing them to fit in the submarine's tight hangar. The crew could assemble and launch all 3 aircraft in just 45 minutes, even in rough seas. These planes were meant to carry out surprise attacks on the Panama Canal, but the war ended before they could complete their mission. The I-400 submarines pushed the limits of 1940s technology. Their hangar was nearly 100 feet long and sealed against the ocean depths with massive hydraulic doors. A compressed air catapult could launch planes in waves up to 18 feet high. The submarines even carried spare aircraft parts and enough fuel for multiple missions. But maintaining aircraft at sea proved nightmarish. Salt air corroded delicate instruments, and humidity wreaked havoc with wooden aircraft components. The planes had to be constantly maintained, their engines turned over regularly to prevent seizing. Launch operations required the submarine to remain surfaced and vulnerable for precious minutes. While the Japanese actually built their underwater aircraft carriers, the German Type XXVI submarine represented a different kind of ambition. Designed in the final months of World War II, it would have been the world's first true submarine, capable of staying submerged for its entire patrol. Previous submarines were really surface ships that could submerge for limited periods. The Type XXVI would change that forever. The heart of this revolution was the water propulsion system, named after its inventor Helmuth Walter. Instead of conventional diesel-electric power, it used hydrogen peroxide as an oxidizer in a closed-cycle steam turbine. This system produced unprecedented underwater speed, up to 25 knots submerged, faster than many surface ships. But hydrogen peroxide was incredibly dangerous. Even a small leak could trigger an explosive reaction. The Germans learned this the hard way during testing, when several prototype engines exploded spectacularly. The fuel was so volatile that a single drop on organic material could cause spontaneous combustion. The Type X XVI also featured other revolutionary innovations. Its hull was streamlined for underwater speed, abandoning the compromises of earlier submarine designs. The conning tower was minimal, reducing water resistance. Even the torpedo tubes were redesigned for better hydrodynamics. The submarine's battery system was also revolutionary, with higher capacity than any previous design, allowing for extended underwater operations. Construction began on 4 Type XVI submarines in early 1945, but none were completed before Germany's surrender. Yet the concept proved sound. Post-war navies would adopt many of its features. The teardrop-shaped hull, high-speed underwater propulsion, an emphasis on submerged operations would become standard in modern submarines. The water propulsion system itself was a maze of engineering complexity. The hydrogen peroxide fuel, called Ingolin by the Germans, was concentrated to 85% purity. At this concentration, it became a powerful oxidizer that could drive the submarine's turbines at unprecedented speeds. But this same chemical energy made it lethal to handle. Special tanks, pipes, and handling procedures had to be developed just to store the fuel safely. The system worked by decomposing the hydrogen peroxide using a catalyst, producing superheated steam and oxygen. This mixture drove a turbine at extremely high speeds, providing more power than any conventional submarine engine. The oxygen produced could also be used for the crew's breathing supply, extending underwater endurance. But the challenges didn't end with propulsion. The Type XXVI's advanced sonar system required extensive sound isolation to prevent interference from the high-speed turbine. The hull had to be strengthened to handle the stresses of sustained high-speed underwater operation. Even the crew quarters needed special ventilation systems to handle the heat generated by the water machinery. These underwater experiments, the Soviet Project 664, Japanese I-400, and German Type XXVI, shared a common thread. Each pushed the boundaries of what was possible beneath the waves. Each solved incredible engineering challenges, and each ultimately proved too complex, too expensive, or too dangerous for practical military use. The Soviets never built their submarine aircraft carrier, realizing that the concept was obsolete in the age of nuclear weapons. The I-400s were scuttled by the US Navy after the war, their technology too dangerous to fall into Soviet hands. The water propulsion system would be studied by several navies after the war, but its inherent dangers led to its abandonment in favor of nuclear power. Yet these vessels left an enduring legacy. The I-400's aircraft handling systems influenced the design of missile submarines. The Type XXVI's hull form became standard in modern submarine design. Even Project 664's ambitious aircraft launch system contained ideas that would later appear in submarine-launched cruise missiles. The costs of these experiments were staggering. The I-400 program consumed resources that could have built dozens of conventional submarines. The water propulsion research cost Germany millions of Reichsmarks and countless hours of engineering talent. Project 664's design phase alone tied up hundreds of Soviet naval architects and engineers who could have been developing more practical vessels. The human cost was equally severe. Several test pilots died developing aircraft launch systems for the I-400. The water system's development claimed multiple lives through hydrogen peroxide accidents. Even routine maintenance on these experimental craft proved hazardous, with crews exposed to toxic chemicals and dangerous pressures. The story of these underwater oddities highlights a crucial truth about military technology. The line between innovation and impracticality is often razor-thin. These submarines represented the outer limits of what was technically possible, but they crossed the boundary of what was militarily practical. Their designers reached for capabilities that, while theoretically achievable, proved too complex and risky for actual combat operations. While these ambitious vessels never fulfilled their intended roles, their greatest impact wasn't on naval warfare. It was on the future of military development. Their stories would teach military planners crucial lessons about the true cost of technological ambition. The story of these never-realized war machines reveals a pattern that military planners still struggle with today. In each case, whether it was Hitler's massive tanks, America's nuclear-powered fighting vehicles, or submarine aircraft carriers, engineers became caught up in what was technically possible rather than what was practically useful. The financial toll was staggering. The Land Cruiser program consumed resources that could have built hundreds of conventional tanks. The Hughes 84's budget could have purchased an entire fleet of proven cargo aircraft. The Soviet Union's Project 664 submarine tied up crucial naval engineering talent for years. But the true cost wasn't just monetary. It was the opportunity cost of what could have been built instead. These projects shared common fatal flaws. First was complexity. Each machine required multiple new technologies to work perfectly together. The TV-8 tank needed both a functional nuclear power plant and a revolutionary crew protection system. The XP-79 flying ram required advances in metallurgy, pilot protection, and aerodynamics. When one element failed, the entire concept collapsed. Size was another consistent problem. The Rat tank was too heavy for bridges. The Spruce Goose was too large for practical operation. The I-400 submarines were so big they sacrificed the stealth that made submarines effective. Military planners learned that bigger wasn't always better, and was usually worse. The timing of these projects is particularly telling. Most emerged during desperate circumstances. Nazi Germany's final years, intense pressure of the Cold War arms race, or the urgent needs of World War II. This desperation led military leaders to grasp at technological silver bullets, hoping for wonder weapons that could turn the tide of war. But perhaps the most important lesson was about human factors. The Land Cruiser would have required a crew of 40 men working in perfect coordination. The Object 279 tank's complexity made maintenance a nightmare. The Walter submarine system was so dangerous that routine operations risked catastrophe. The best weapon isn't just the most powerful. It's the one soldiers can actually use effectively in combat. These projects also reveal the dangers of over-specialization. The BV-40 glider could only perform one specific type of attack. The I-400 submarines sacrificed traditional submarine capabilities for their aircraft-carrying role. The Gustav Gun required an entire railway system just to move into position. Military historians would later conclude that versatility and reliability trumped specialized capabilities in actual warfare. Modern military development still struggles with these lessons. The F-35 fighter program faced years of delays due to software complexity. The US Zumwalt destroyer program was cut from 32 ships to just 3 due to spiraling costs. The Army's Future Combat Systems program was cancelled after spending $18 billion on ambitious but impractical vehicle designs. Yet these failed projects weren't complete wastes. Many of their innovations found their way into successful weapons. The Type XXVI submarine's whole design influenced modern submarine development. The materials science developed for the Spruce Goose advanced aircraft construction. Even the Chrysler TV-8's closed-circuit television system predicted modern tank optics. The psychological impact of these projects shouldn't be underestimated. They consumed not just resources, but also the time and energy of some of the finest engineering minds of their eras. German engineers working on the Land Cruiser could have been developing more practical weapons. American nuclear scientists assigned to the TV-8 could have been advancing submarine reactor technology instead. The true legacy of these bizarre war machines isn't in their failure, but in how they pushed the boundaries of what was possible. They marked the outer limits of military technology in their eras, helping define the line between ambition and practicality. Their stories continue to influence military planning, reminding us that the most effective weapons aren't always the most impressive on paper. From tanks as heavy as battleships to wooden aircraft longer than football fields, these war machines represented some of humanity's most ambitious military dreams. While they never saw combat, their stories help us understand the crucial difference between what we can build and what we should build. If you love military history like I do, subscribe for more content like this.